Hey guys, welcome to day 15. Last time we talked about how to use analytical or algebraic approaches to simplify a limit. Now this involves quite a bit of factoring and simplifying functions until you got to a function that had the same properties except for that value, right? That was theorem 1.7. And the thing is, that's a really, really powerful tool that is utilized a lot. Like if you're taking calculus next year, the first chapter, you will utilize that tool a lot. Okay, huge amount. However, there will come times where you can't simplify algebraically using those techniques. That does not mean there isn't an algebraic way to solve the problem. It just means that those particular techniques of factor and simplify aren't going to work. You have to use different algebraic techniques. And today, I'm going to talk about one of them, just one, that is really versatile and powerful and helps to kind of fill in some of the gaps on problems you can't do this with. So without further ado, let's take a look. For today, I want to look at this limit. Now obviously with this limit, we could solve this using the numerical approach, where we approach zero very much by hand, or you could do it with the graphing approach. Now keep in mind, the reason why I harp on the analytical approach so much is because depending on the school you go to, or the test you're taking, just quick side note here, I teach AP calculus. Many other schools do. Some teach dual credit. Depending on the school you go to, you may not be allowed a calculator for your problems. And if that's the case, then doing it numerically is almost impossible. Doing it graphically is very, very difficult, especially if you don't know how to simplify it first. Because I don't know about you, when I look at this problem, I don't know how to graph that. What do I do? Like, it doesn't make any sense, okay? And so the analytical approach is prioritized over many others because of that basic need and skill set that you want to use. So keep that in mind when you look at some of these problems, is that yes, you could obviously solve it the easier ways. But if you're taking the AP test, they have these all the time, and they have a specific portion of the AP exam which is no calculator. And they expect you to do it by hand. And I don't know about you, I'm not plugging in negative 0.0001 into that equation and try to get an answer. It ain't happening. Right? I can't do that square root by hand. Nor can I subtract from it and then divide by that nasty number. Like, it ain't happening. Okay? So keep that in mind. Many of these approaches are designed that way to get around that fact. And so, take a look. If those previous techniques are not viable, right? There's nothing to factor here, right? I can't take an x out and cancel with the bottom, which would be what I'd want to do. So how do we solve this? Well, today's big material is about what's called rationalizing. Rationalizing. Ooh, I can't spell. Rationalizing. What this means is using a conjugate to rewrite a problem. Now, if the word conjugate appears, similar, or like you've seen it before, that's a good thing. It means your algebra teacher did well, okay? A conjugate is a very specific fraction that's designed to manipulate this original function. Now, with this problem, the conjugate I'm going to use, I'm going to conjugate kind of different than how you'd normally do in algebra, right? We use conjugates in algebra to get rid of things in the denominator, but for us, I'm actually going to get rid of the thing in the numerator, which seems backwards, but actually works really well. Now, how I'm going to do that is I'm going to use the very specific fraction that matches the top in every way except one. Notice how this conjugate, the big thing about it is what happens right here. Okay, first of all, to get this conjugate, we duplicate the nasty. Nasty. Okay, find the nasty part. So in this case, that's the top, or the numerator. We duplicate that, but we flip the middle sign. When I say middle, this is one term, right? The square root of x plus 1 is one thing, and then this is the second term. The 1 is a second term. So we flip this symbol that is in between them from negative to positive. We simply change that sign. Notice the negative inside isn't going to change because we don't want it to. That's not how a conjugate works. You have to flip the middle piece. And so of these two pieces, we have this piece, which is the first piece. We have this piece, which is the second piece. And now notice how we did that on top, but also on bottom. This is because mathematically, this is equivalent to 1. So we are essentially multiplying by 1. Remember, because anything divided by itself always becomes 1 with the exception of 0. And so this statement is multiplying by 1, which is allowed algebraically. Now watch what this thing is going to do when I multiply them. So I'm still going to have a limit, and the x is still going to approach 0. On top, I'd have the square root of x plus 1 minus 1 times the square root of x plus 1 plus 1. On bottom, I'd have x times the square root of x plus 1 plus 1. Now you can easily see here that, of course, if I was to go ahead and cancel right now, I get right back where I started, but I'm not going to. That is because my next step is going to be, okay, roll this out. Simplify this, okay? So that's what I'm going to do. I'm going to take this piece times the first piece and the second piece. The negative 1 times the first piece and the second piece. And on bottom, I'm going to do the same thing. I'm going to take x times the first piece and x in the second piece. It's going to give me a new limit. Well, new being relative. And I will note, you should probably FOIL out the top. The bottom should probably stay. Like this bottom step, I'm going to skip. I would not recommend doing that step, just because if our goal is to cancel, then I should leave the top in factored form. So there we go. So I'm going to leave the bottom. Remember, my goal was I want to get rid of the nasty, right? I want to get rid of this nasty using a conjugate. So the top's the nasty, so I do the top piece. The bottom's not the nasty piece, so I'm going to leave the bottom the way it is. Now on top, let's watch what happens. Square root of x plus 1 times square root of x plus 1. Hopefully you remember your algebra. This would become x plus 1, because squares and square roots cancel. Square root of x plus 1 times positive 1 will become positive square root of x plus 1. Negative 1 to the square root of x plus 1 would become minus square root of x plus 1. And then negative 1 times positive 1 would become negative 1. You'll notice that on top, you end up with some pieces that are naturally going to cancel, leaving you with the limit as x approaches 0 of, on top you'd have x plus 1 from the first parentheses, minus 1 from the second, all over x square root of x plus 1 plus 1. Now you notice again on top some things are going to fix, right? The plus 1 and the minus 1 are going to fix, leaving us with the limit as x approaches 0 of x over x, parentheses, square root of x plus 1 plus 1. And again, things are going to cancel. The whole point of using this conjugate is that if you do it correctly, a bunch of stuff ends up canceling, leaving you with this new limit. Limit x approaches 0 of 1 on top, and on bottom, square root of x plus 1 plus 1. Now you might look at this in the algebra sense and be like, wait a minute, I remember my algebra teacher. We're not supposed to have a radical in the denominator. You know what calculus says? Suck it. We don't care. Because this one, you'll notice I can now actually evaluate. This becomes 1 over the square root of 0 plus 1 plus 1. And when I evaluate that, I end up with 1 over square root of 1 plus 1. Square root of 1 is 1, so this becomes 1 over 2. This is evaluatable. Whereas remember, the original equation, if I plug in 0, I end up with a 0 in the denominator, which is not allowed. This one cannot be solved. This one can. Yes, your algebra teacher would be angry. I cannot emphasize enough. If you're an algebra teacher, you're like, ah, what are you doing? How could you? You betray me. But this can be solved. That one can't. And so we rationalize using a conjugate to get to a variable that is solvable now, which again was not possible with what we were given before. That's the big detail. Remember, the idea of a limit is to be able to solve. Part one, end of story. You have to be able to solve it. If I can't solve it, it can't be done. Okay? This, not solvable. This, solvable. Yeah. Okay. Notice the steps before we go on. We're going to do another one of these because we need some practice. We're going to end up doing 3 of them in total. Okay. Look again. We started with this nasty thing that was not solvable. We try to plug in 0. We get 0 in the denominator. Not allowed. So we use a conjugate. We use a conjugate of the top piece. We use a top piece on top and bottom because that's multiplying by 1, which is allowed. When we do that piece, we then FOIL at the top but leave the bottom alone. So we FOIL this thing out, becoming this equation. We simplify, we cancel, we're left here. Algebraically, this one can be done. We plug in 0. So 1 over the square root of 0 plus 1 plus 1, and then we simplify, getting down to 1/2. And that is the correct answer. Taking a look at Desmos here. Okay, my original equation was, on top we have the square root of x plus 1. Outside we have minus 1. And that's all on top, divided by x. This is what this equation looks like, and you can clearly see here, like, based upon the picture, it looks like it's going to 1/2, but again, at 0, it's actually undefined. What equation did we get when we simplified this? If I look at my paper, I got 1 divided by square root of x plus 1 plus 1. Notice these are the exact same equations, but this blue one has an answer at 0 and it's 1/2. So these is, again, this is theorem 1.7. See, we have the exact same equation, exact same graph, but the blue one has an answer at 0. The red one does not have an answer at 0. And so we use the blue one and the analytical approach to be able to get that answer, which says that at 0, the answer should be 1/2. Okay, this is referred to as rationalizing. It's a very powerful tool. It allows you to take a function which is not solvable. I cannot emphasize that enough. I will yell it if I have to. This is not solvable. I plug in 0, it doesn't work. I rewrite it in a form that is the exact same, but is solvable. That's where I get the 1/2 from. Okay, let's keep this here. Use it as my guide. Let's go to the next one. Okay, I'm ready. We have, as our next example, you'll notice that many of these look very similar. That's because they are. You often notice there's patterns when it comes to using these particular techniques. So I have that there, square root of x plus 2 minus square root of 2 over x. All of your ones at your homework look very similar to this, with very few exceptions. I'll show you the one exception here in a little bit. Okay. So, in this example, we trade this in, we try it out. So this time, again, we're going to multiply by a specific conjugate. That conjugate is the nasty piece, which is the square root of x plus 2. But now we're going to be using the conjugate. So we plus the square root of 2. And we do that same piece on top and bottom, because remember, this piece is equal to 1. And so we're allowed to use that conjugate. Now, what happens? On top, we get the limit as x approaches 0 of square root of x plus 2 minus square root of 2, that's our first piece, times our second piece, square root of x plus 2 plus square root of 2, all over x times square root of x plus 2 plus square root of 2. Now before I go on, remember, the only reason we're doing this is because the original was not solvable. I plug in 0, 0 plus 2 is 2, square root of 2 is square root of 2, square root of 2 minus square root of 2 is 0 on top, and on bottom we just get 0. We can't divide by 0. You cannot plug this in. So you cannot plug in to the original. That's why we're doing these steps. Okay? So now we're here. On top, we're going to follow this out. Now, the reason we're using the conjugate is, if you remember how to use a conjugate, it's difference of squares. So this becomes x plus 2 minus 2. And on bottom, x square root of x plus 2 plus square root of 2. And then we simplify some more. On top, we end up with just the limit as x approaches 0 of x over x parentheses square root of x plus 2 plus square root of 2. All right. From here, we cancel out the x's, leaving just the limit as x approaches 0 of 1 over the square root of x plus 2 plus the square root of 2. Now, there's an important note to make here. If I plug in 0 here, it doesn't work. If I plug in 0 here, it doesn't work. If I plug in 0 here, it doesn't work. Only once I've gotten this far can I actually plug in 0 like we know we want to, and I'll actually get an answer. And your algebra teacher would throw a fit, but I stop right there because lazy, okay? Don't hurt yourself. You've already done all this beautiful math. Just stop, okay? This is a fine answer. Math teachers all over the world would be like, yay for you. You got the answer because you did the hard part. In calculus, we're here to test this process. We don't care as much about that process. Okay? Let's do one more. It's a little bit different, but it follows the same trend. Limit as x approaches 16. Oh, that's the first time we haven't approached 0. So we have on top 4 minus the square root of x. On bottom, x minus 16. So again, you notice if I plug into this function, I don't get an answer. On top, I get 4 minus the square root of 16. Square root of 16 is 4. 4 minus 4 ends up being a 0 on top. On bottom, 16 minus 16, 0 on bottom. So again, the original isn't working. So what do? I multiply by the conjugate. So that would be 4 plus the square root of 16. The square root of x, I should say. All over 4 plus the square root of x. So we're going to use the conjugate. On bottom, this gives me x minus 16 times 4 plus the square root of x. We still have a limit. As x approaches 16. On top, I'm going to go ahead and simplify. 4 times 4 would give us 16. Negative square root of x times positive square root of x would give me negative x. Now here's the thing. You notice that these two are very similar. By the way, I just shortcutted that. I just multiplied them. Well, if you get good, that's what you're supposed to do. The top here is equal to negative 1 times x minus 16. So these two are the same thing, just with a negative sign. So this becomes the limit as x approaches 16 of negative 1 over 4 plus the square root of x. So again, notice, I rewrote it so that I could cancel with the bottom specifically. Because remember, the problem is I can't divide by 0. I don't care what the top is. I care if I divide by 0, because dividing by 0 is not allowed. So I cancel with the bottom by using this negative 1. These two end up canceling, leaving a negative 1 on top, and on bottom we end up with a 4 plus the square root of x. And you notice that now I can plug it in. I actually do get an answer. I have negative 1 on top. 4 plus the square root of 16. This becomes negative 1 over 8. Square root of 16 is 4. 4 plus 4 is 8. And again, if I go back to my original equation, and I go to like something like Desmos, let's take a look before I do. But if I go back to Desmos, I do get the same graph in these two equations. Let's see. First equation was 4 minus square root of x divided by x minus 16. So this isn't exactly a very interesting equation. It doesn't do a whole lot. You notice that it's equivalent to negative 1 divided by 4 plus square root of x. Those equations are exactly the same. The difference is at 16, there's no solution on the red line, but on the blue line, there is a solution. Negative 0.125, which is of course negative 1/8. And so again, the goal becomes, can we find this graph, this g of x, as we called it, where they end up being the exact same function? But one of these, if I plug in 16, I get an answer. This one, if I plug in 16, I get an answer. Whereas in the other one, if I plug in 16, I do not get an answer. So again, it's about finding that alternative function and then allowing us to plug that number in until we get a solution. Now there's one more weird use of this conjugate rule, and it has to do with fractions inside of fractions. Let's take a look at our final example today. It'll be a fun one. And that final example is give me a second. Where's our book? Here's the book. Okay. I'm actually going to do one of your homework ones because I think it's worth doing one of your homework ones. Okay, that's the homework problem. And this is number 59 in your homework. Okay, number 59 states we have the limit as x approaches 0 again. Oh, that's nice. Of, let's see, this is written in a weird way. So I'm going to tell you how the homework writes it. 1 divided by 3 plus x minus 1 divided by 3 all over x. Now, it's important to note before I continue that if you were to write this out correctly, this is what this would look like. Limit as x approaches 0 of 1 over 3 plus x minus 1 over 3 all over x. This is another one where we're going to use a conjugate in order to solve this, but in a very strange way. Our goal this time is we're going to multiply by both fractions. What this means is we're going to take the denominator of both fractions and multiply them. So the first denominator is 3 plus x. The second denominator is just 3. And we're going to do it on both the top and the bottom. Okay. So notice how I chose these. I just multiply by both fractions denominators. So what that's going to do is actually pretty neat. On top, we'll just go ahead and write out what it would do. We would take the top piece, 1 over 3 plus x minus 1 over 3 times 3 plus x times 3 all over x times 3 plus x times 3. Like, obviously these two are the same because if I cancel them out, I get the same results. But watch what happens when I distribute. Remember, when I distribute, I have to distribute to both terms. So take These 3 plus x times both fractions, and this 3 times both fractions. I have to do it to both of them. So let's start with the 3 plus x. Once again, on bottom, it's going to stay pretty much neutral. It's going to be x times 3 plus x times 3. Okay, on top. 3 plus x times this fraction. We'd have a 3 plus x on top and a 3 plus x on bottom, meaning we end up with a 1 here. The 3 plus x and the 3 plus x are going to cancel, leaving a 1. We then multiply by 3, leaving us with a 3. Again, I cannot stress enough, this is where we get some algebra that really has to stick with you. Okay? If I take the 3 plus x and multiply it by this fraction, the 3 plus x and 3 plus x are going to end up canceling, leaving us with 1, and we take 3 times that 1 to get 3. Minus the second parentheses, okay? So what we've done is we've taken, we've taken this fraction times these two numbers. The 3 plus x and the 3 plus x are going to cancel. 1 times 3 gives us 3. Minus, now we do the other piece of this fraction. We take the 1/3 times the 3 plus x and the 3. Now the 3 and the 3 will end up canceling. And we do 1 times 3 plus x, giving us 3 plus x. So notice how we got rid of these both fractions in one step using this very specific multiple. We got rid of the 1 over 3 plus x and multiplying by 3 plus x. We got rid of the 1 over 3 and multiplying by 3. But because we can't just do it to one of them, we have to do it to both of them, giving us this new equation. And again, this equation is equivalent to this equation, which is equivalent to the new equation. But the new equation, you'll notice, just like all the other ones, will simplify. On top, we distribute the negative signs. This becomes negative 3 and negative x. Negative 3 and negative 3 makes 0. We end up with negative x on top. On bottom, we have x, 3 plus x, and 3. Just like before, the negative x and the x are going to cancel, leaving us with the limit as x approaches 0 of negative 1 over 3 plus x times 3. Again, if I plug in 0, I get no solution because I'm never allowed to divide by 0. But if I plug in 0 here, I do get a solution. This would be 9. Plugging in 0, 3 plus 0 is 3 times 3 would be 9. So again, this works. As weird as it looks, it works. This is your alternative pathway to get to your numbers. In both cases, we're multiplying by something very specific. So in the first case, we're multiplying by this conjugate. In this new case, we're multiplying by these specific fractions. The goal should be to always get rid of these nastiness. The goal should be to get rid of the nasty. So I multiply by the 3 plus x, that gets rid of the 3 plus x. I multiply by the 3, that gets rid of the 3. There's some extra pieces that end up appearing because of that, but those pieces end up canceling, which is why this is such a good technique. It's because if it's done correctly, you will always get to an equation that is the exact same equation as the original, but is actually solvable. Let's go back to Desmos. We're going to type in this equation, see what it looks like. Then we'll type in this equation, verify they're the same thing, and show why it's 0. This one's negative 1/9. Here's Desmos. Alright, my equation was 1 over x plus 3 minus 1 over 3 divided by x. Look at that thing. That's cool, I guess. Now let's look at the one we got in return, which was negative 1 over 3 plus x times 3. Notice again, these two are exactly the same. However, the red one, if I go to 0, is undefined. But the blue one, if I go to 0, it is negative 0.1111, which is negative 1/9. And so again, We use these techniques to find this alternative g of x, which is solvable, compared to the original, which was not. This will be a tough day, because there's a lot of algebra techniques that you really have to have down. There's a lot of multiplication and simplifying. It's tough. I look forward to hearing your guys' questions and seeing what you guys can do. But that'll be it for today. One topic, just rationalizing these fractions, and a relatively short assignment afterwards. But otherwise, that's it. I look forward to hearing you guys' thoughts and comments, and I'll see you guys at our Zoom session this afternoon if you can be there.